All right, so let's take a look at this. We've been trying to just use the definition in order to come up with some way of finding the variance. And the reason why I had you do this is because I don't want you just to memorize some formula. Because frankly, the formula can be a little bit tricky to memorize and get straight. But if you understand this definition, then it actually is not this great mystery, okay? The variance, which we use either an S, hang on. We usually use either an S if it's a sample variance, or we use a lowercase Greek letter sigma if it's a population variance, okay? But in either case, we have a mean. Now, when you're finding the mean of stuff, what are you doing?
Averaging.
Okay, what does that mean?
Adding them all together and dividing by the number of numbers due.
Okay, you're adding up a bunch of stuff, and then you're dividing it by however many things you have, right? Okay, so now, here's where our grammar helps. Look at the mean of. What's this prepositional phrase? What are we taking of all of this? Well, of in this case is telling us this is an adjective prepositional phrase, modifying mean, because it's telling us what mean we're actually taking. Okay? So it's the squared differences. So we're squaring something. Okay? And differences means, what are we doing?
Subtracting.
We're subtracting. Okay? Now, the squared differences from the mean. So the mean is that x bar. What are we subtracting from the mean? That's right, the individual scores. Okay? So I'm going to do the sum from I equals 1 to n of x sub I.
Wait, I have a question. So where did the of fit in?
Of is just introducing this whole prepositional phrase that modifies mean. It's telling us what mean we're taking.
Right, but is that into the brackets then? Like the brackets being multiplied by the sum?
Well, it's not this being multiplied by the sum. We're taking the sum. You got to take the sum of something.
Okay.
Okay? Well, we're taking the sum of all of these differences then squared.
Yeah.
Okay? Now, there are actually a couple of different formulas for means, or for variance. Okay? They come out with the same values. For the most part, this is the population variance that we're talking about. Okay? The sample variance you actually divide by n minus 1. And the idea there is you divide by a little less to give you a broader, it gives you a little bit bigger of a number. Since you're dealing with a sample, you're a little less sure, so it gives you a little bigger of a number. We're not going to get into the particulars of that. If you took AP Stats, you would, but for our purposes, we don't really need to worry about that difference so much. But that's the breakdown of this definition. Okay, so you found the mean of these 5 values, which was what?
394.
Yeah.
Okay, 394. So that's your x bar. Okay? Now, looking at the values, we're talking about a measure of spread. We said variance is a measure of spread. How spread out is our data? Looking at those numbers, what would you expect from your variance? Are these numbers all kind of grouped together, or are they spread out? They're pretty spread out, okay? So we can expect our variance to be somewhat spread out, okay? So we're now going to take each of those scores and subtract them from the mean. Now, obviously, some of them are going to end up positive, some are going to end up negative. Okay, for example, 394 minus 600 is a negative 206. And 394 minus 470 is a negative 76. Okay, 394 minus 170 is 224. 394 minus 430 is 36.
Oh, so you're, oh.
And 394 minus 300 is 94. Okay, now here's the deal. If you accidentally did that backwards, it doesn't matter. Why? You're going to square these anyways, right? So you square it, My guess is on one of those, if you had the negative and then you hit the square button.
I put the positive values in.
You did? Okay,
I just squared them together because I knew it was gonna end up being positive anyway.
good. And that's really what you ought to do. And if you know it's going to be positive, don't bother hitting the negative sign because you're just, if you hit negative 3 squared, it's going to square the 3 before it applies the negative.
Yeah.
Okay? To square a negative 3, you have to put the negative 3 in parentheses.
Yeah.
So I just say, if you're squaring it, don't bother put the negative in. Alright, so there is the sum of the squares. Then we have to divide that whole thing by 5, because there are 5 scores. Okay? Does that make sense?
That's what I did.
And you got, what, 71,000?
Yeah.
21,704.
21,704. Whoop,
Why did I get that?
I'm being lazy. Let's fix that. 21,704.
I know what I did
Okay.
wrong.
What's
I
that?
got all of the numbers the same except for 36 squared. I got 136 squared.
Oh, okay.
No, I was right. Yeah.
Okay. Alright, so does that make sense? I want to kind of remove some of the mystery on the formula. A lot of times people just try to memorize this formula and it doesn't make sense and they end up forgetting a piece or whatever. If you understand the definition, it's really not that hard of a formula to use or remember, okay?
I actually like that. That helped me a lot understand that formula. 'Cause otherwise I would have looked at that and been completely confused.
Good, I'm glad. Alright, so now let's talk a little bit about standard deviation. Variance is actually not incredibly useful, except for the fact that it gives us our standard deviation, okay? Now, I think before I accidentally gave wrong notation, variance can be written, if we're talking about a population variance, we write it as sigma squared. Okay? That's our variance. Okay? Sigma is the standard deviation. You'll also see it as S and S squared. Okay? If we're talking about samples. Now, the standard deviation is really the measure of how spread out the numbers are. It's a mean distance each score is from the mean. Okay? Now, just looking at our notation, how do you think we find standard deviation?
Square root of variance.
Exactly. It's the square root of the variance.
So wants to know if you have scrap paper at all.
The standard deviation tells us, well, like you see here, the mean distance, each score is from the mean. If I have, say, a mean right here, and I've got all these scores that are kind of all spread out, okay? Each one of those has a different distance, obviously, from the mean. Like there's that distance, that distance. Some of these are below. We actually don't care about above or below, all right? But we have all these distances, okay? And what the standard deviation gives us essentially is the mean of all of those distances. Okay? So, and what that tells us is, let's say we have a mean,
Direction and spread then.
huh?
It probably can tell you which direction it's spread.
But not which direction, because actually, because you're talking about it from the mean, you're gonna have an equal distance above as you would below, total, okay? That's why we have to square it in the variance, and then we square root it for the standard deviation, because if we didn't square it and we added them all up, guess what they would add up to? 0. Because the mean is the central value. So if I added up all the distances positive, to the right of the mean, and I added up all the negative distances to the left, I'd get 0. So that's why we square it, to force them all to be positive, and then we square root it here to get the standard deviation at the end, okay? Now, one thing to understand about standard deviation is that, here's kind of a technical thing here. It says it's a non-resistant measure of spread. In other words, it doesn't have anything built into it to resist being impacted much by extreme data values, okay? And that's why if you have skewed data, the standard deviation is a little less reliable. Okay, it is very useful and reliable when we're dealing with things that are normally distributed. Okay, now we briefly mentioned normal distribution and stuff last year in pre-cal honors. We're going to revisit that again, don't worry. But standard deviation is super helpful when we're dealing with normal distribution stuff. Okay. So, here's our formula. You can see this formula looks very similar, although notice here, they have this the reverse of how we had it. Doesn't matter because we're squaring it. And honestly, you'll see it written both ways. Okay? There are also other formulas out there that you'll find that do give you the same number, they just get it a little different way. But this is the formula that the IB uses. So now here's a little thing, and we're not going to make a huge deal about sample versus population. But I would like you to understand the notation, okay? Particularly like as you're writing your IA, if you do a statistics topic, make sure that if you're talking about doing a sample, you're using notation for a sample. If you're doing notation if you're talking about a population, make sure that you use the notation for a population, okay? So here you'll notice, okay, the sample stuff is all just our regular alphabet. The population is the Greek alphabet, okay? So you have the X bar for mean versus the lowercase mu for population. You have variance as S sub n squared. For a sample, for population, it's sigma squared, okay? And then, of course, standard deviation for a sample is S sub n, population is sigma, okay? I do want you to know that notation. All right, you need to be able to use that proper notation, okay? So just be aware of that. But this is just kind of summarizing what we've already looked at here, what the formulas are, okay? Now, here's our data from our survey that you can't possibly read. And it's not in your notes there. I just input it after we got it. So I want to practice. This is the survey, the questions you guys came up with. So I thought a couple of these might be useful for us to do. Whoops, let me get rid of that and zoom in a little bit. Okay, so let's do.
Are these on notes somewhere?
These are not on the notes. I just input this data because we just collected it.
Okay, so when you were referring to standard deviation and variance with the, is that the omega sign?
The sigma.
The sigma sign? That's because you were doing it in the
You
population.
said 4.
Yes, sigma. Any Greek letters are population.
Okay.
Our alphabet is sample. Okay. All right. So let's do a couple of these here, just to practice, and let's also kind of surmise what we think it would be. Here's one.
Someone's like 13. Someone's in their immediate family.
This is how many hours of sleep you get on Saturday.
That was 6.
Okay. So here goes, our range goes from 6 up to 12. All right. What would you expect though for the standard deviation of this? Would you expect it to be pretty big or somewhat small? Okay, somewhat small. Anyone have an estimate? Just a guess.
3.
3?
6.2.
6.2
For what? 2.
for the standard deviation.
Oh,
No, it could possibly be.
I don't know. Let's see. Go ahead and try this. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 pieces of data in this one. Okay?
So many numbers.
And you want us to find the standard deviation?
Yeah, go ahead and try to find the standard deviation. If you want to work with somebody to kind of crunch the numbers, you can do that. You can also use the lists on your calculator,
I don't know.
if you remember how to use the lists.
Mode?
They have the curly brackets.
Oh, got it. You're spelling me first, right?
How many pieces? 19?
Mm-hmm.
Is what you mean?
Wait, how many did we say? Oh, they're 19.
19.
So you're just gonna do each number, right?
Yeah.
But I do that, I just find like 1 for 10.
How many significant figures do we round into?
Huh?
Always do 3 significant figures. Just get used to doing 3 for the whole year. All right, so let's take a look at this, and I'm actually going to do it on my calculator with the lists, so that you guys can see how to do it on the calculator. I'm gonna show you the camera here. All right, I'll try to keep it steady. First of all, notice the lists. We have these curly brackets. That's shift parenthesis.
Is this on your home screen, or did you just go to a certain?
Huh?
Did you have to?
This is on my phone. This is that web at EMU
Oh
app.
wow, I didn't even notice. If it's
Yeah.
Wow. Oh.
So, and then in the list you separate the values by commas. Okay, and then when you hit enter, it'll do it. Now I stored it as L1. Okay, you can see down here above the 1, 2, 3 through 6, they have L1, L2. That's a variable built into your TI-84 to store lists in. Alright, so the first thing that we need to do is find the mean, right? So I'm going to come over here to my list menu, so list, and then I'm going to find the mean, okay, of that L1. Okay, so did you guys get 8.94736 and so on?
Yep.
Okay, now as we're going through this, should we round that?
No.
No, we should use that value. Okay? That is one thing. Remember I said when you're doing the IB exam, if you have like a part A, which was find the mean, you would round your answer for part A to 8.95. But if you were then using that in finding your variance, you want to use the unrounded portion. So that's where storing that value might be helpful. So like down here you have the STO button, STO. We're going to store that in the variable X or N, sure.
But for each number that we get after, like.
Oops,
do we
it didn't
keep
like
whole
that.
thing or do we round?
Let's store that in. Sorry, hang on one second. I don't
It's all good.
store that in A. So there's our mean stored in A. Okay, what'd you ask?
I said for each number that we get, so like for example the first term is 10. So you do 10 minus that squared. And it's like 1.108033241. You keep that whole thing?
Keep that whole thing. That's why you want it in your calculator, okay? And this is where the list actually can be super helpful. Because look, now what I can do is I can take my list, and if I do minus the mean, which I stored as A, it's going to subtract that from all the things in the list.
How do you get the list set up though?
With those curly brackets
Where?
Yeah, how do you,
above the parenthesis sign. See that? You hit second parenthesis.
Oh, then you just have,
Ah,
and then you just
okay.
have all the numbers?
And then you separate each element with the comma.
Oh, so that's how you just form a list.
That's how you form the list, and then I stored it. I hit stow.
Okay, so there's
L1.
you don't have to go to like mode or math.
No,
or
no, no.
Okay. I thought we had to do that.
Alright, so here I have all of those differences.
Different numbers now.
Okay? I have all those differences. Now mine are all the opposites of what yours were, because I did the list scores minus the mean rather than the mean minus the scores, but that's okay, because what do I do next?
Square.
I square them all. So I just hit squared, and when you do this with a list, it'll take every element in the list and square
So
it.
that gives you the x sub I minus the mean of the score squared. That's
Exactly.
the brackets of the, okay.
Yep. So now what do I have to do with all these?
find the mean?
Put it
Yeah, add
on
'em.
top.
I add them up.
Add 'em up.
I add them up. So now I'm going to go back to my list menu and operations. And if I come down here, oh, nope, sorry, it's under math. Sum, number 5. The sum of that list, so I'm going to hit answer, is 56.947.
And then you
Divided
square
by-
root that.
Well, hang
No,
on, what do we do
you
first?
Divide it and then square root it.
We divide this by 19.
I thought that was implied.
Oh, okay then.
2.997. Is this looking familiar?
Yeah.
And then square root it.
Okay. And then we square root that. So
Halfway, like I said.
1.73.
1.
But you get 1.73?
That's what I got.
Alright, sweet.
Okay.
Oh.
So we got a standard deviation. Standard deviation of 1.73. Okay? How many of you were able to get that?
I would have gotten the 2 dimensions.
Good. Good. Alright, does that make sense? Okay? Now, listen, one of the things that's really going to help you on, well, throughout the year, in math in college, in math and whatever math you do for your job, okay, and frankly in any job that you ever have, is going to be learn how to use your tools, okay? In this class, your calculator is your tool. One of the 2 exams you take at the end of the year is calculator active, and there are a lot of things that you maybe could do by hand, but there are a lot of things on that exam, on that paper, too, that you cannot do by hand. You've got to learn how to use your calculator pretty well, okay? If you can learn how to do certain things more efficiently, like using lists, if you've got a whole bunch of things you got to do the same stuff to, you know, that'll really, really help you, okay? It'll help you work much more efficiently. You have much less of a, you are much less likely to make a mistake, okay? One thing I will say, let me actually do this. As you're constructing your list, another way that you can do that, let me get back to the camera here, okay? As you're constructing your list, another thing you can do, instead of using those curly brackets, if you hit second list, oops, hang on, second list, oh wait, hang on, sorry, not second list, just hit stat, and you'll see here edit. If you hit edit, notice here, see that L1? That has my data in it that I had stored in L1. Now L2 has other stuff. If I wanted to put my next set of data in L2, I can just come up here and hit clear and hit enter, and it'll wipe out everything in L2. You see that? Get a little bit closer. So if I want to clear out L1, I come up here to the header, I hit clear and hit enter, and it wipes out everything. I'd recommend doing that, but I can also enter the list in here as well. You know, the 10, 8, and so on. Okay, you just type it in and hit enter, and it'll put it in there. So if you don't like messing with the curly brackets and the commas and that, you can do that. And here it might be a little bit simpler also to make sure you don't have any typos. Because that is the one thing they'll throw you. If you type one number in wrong, obviously all your numbers are going to be wrong. So, okay? Any questions? All right. Stop making you sick. Let's try one more here. That was a relatively small standard deviation, by the way. You know, 1.7 hours. So on average, everyone was within 1.73 hours of the mean sleeping time, which was, what was that again? 8.95. Okay. So you guys are getting on average almost 9 hours of sleep on a, you know, Friday night into Saturday. So, and on average you're within 1.73 hours of that. Okay? Some were further, some were closer, but again, it's an average distance. Let's try another one. Wait. I think my pen disconnected for some reason.
So cool. When are they gonna invent those pens for these iPads?
Probably never. They'll just make you buy these iPads. All right. Let's try this one. How many cookies can you eat at one sitting? What would you expect?
34.
Who said 50?
Jesus.
Oh, no.
Those are probably like some mini Oreos.
All right. So this question had a little bit of interpretation, but what would you expect from this standard deviation?
Larger one.
A much higher one, okay? Because you got, like you said, up to 50.
So Mr. Nixon, when I
And
said
then-
34, It was only because I was taking into account it might be like those Publix cookies, like Gottlieb.
I went off the Publix chocolate chip cookies. One box is like 24 of them.
So I figured I could probably eat about 10 more than he could because I'm, a little bit bigger.
It's true.
That's good reasoning.
But I went ahead.
So, and then you've got a little bird
50.
somewhere who can only eat 2. But
Who's this tool
That's
that's
okay.
at 50 though?
So-
50, come on.
Who can eat 50?
hey, I don't know, someone in third period. Anyways, let's go ahead and try it with these, okay? And by the way, try it with the list. Try it with the list just for some practice. If you don't have the 84, maybe lean over and look at someone who does have the 84. Maybe you can read the data off to them and they can type it in for you.
Can I try the wabbit thing?
Yeah, if you've got it, sure.
It sometimes doesn't work.
Did you use the curly
The
bracket?
app. Sometimes.
Yeah, how would you do that?
How do you use the list one? You just go.
No, you do.
Okay.
Math. Or not math. List. Then math.
What is it?
Okay, so let's take a look here. What did you get for the mean?
Oh, we,
What'd you guys get for the mean?
And then square root it to get the same deviation.
Oh, hang on.
Lou,
Yeah.
what do we get for the mean?
The mean.
12.45.
12.45?
Yes.
Okay, so 12.45 cookies on average, or 12.5 if we're going 3 sig figs. Okay. And then, what did you get for the variance?
136.25.
Okay, 136.25, which would be approximately 136.
Well, the standard deviation is 11.67. Or so 11.7.
Okay, standard deviation would be 11.67, so we'd round that to 11.7. Okay? So that would be our standard deviation for that data. Okay? So kind of a interesting study there. Here you can see, and by the way, when you're doing these, look at your data and think about what your answer should be about. Okay? I mean, I said take a wild guess on how many hours. I mean, the more you do this, the more you'll kind of get an idea. But, think about, should my answer be relatively large or should it be small? Okay? Is my data really tightly grouped here? Or would it be, more spread out? Okay? As you look at some of the other things, here we have on a scale from 1 to 10, I forget what this one was, but they're kind of evenly spread, but they're relatively close. How many games out of 10 is the football team going to win? There's a lot that are kind of around the same value.
4.
But here,
hey, listen, most
obviously we have a big outlier of 27, but how many pets do you own? There, we're not going to have, or we shouldn't have that big of a standard deviation. Now, by the way, on that one, how many pets do you own? Remember we said that the standard deviation was a non-resistant measure? In other words, an extreme value or a skewed distribution can kind of mess up its usefulness. This is a case where we would definitely want to, if we were analyzing this, run the data as is, but then run it again without that 27. Okay? So that we have something that is more representative. Okay? Here's another one. What year did you enter at North Broward? Okay. There's not a large spread of data there. Okay, so, you're going to get a much smaller standard deviation. Alright? So, we'll look more at that data and do some more things with data in the future here, but I think that's good for the moment, okay? This was in case we didn't have data. We already did this part, okay? But just to show you, this is one thing you can do if you're having to do it by hand, setting up a little table for yourself like this, okay? The score, what's that difference, and then squared difference, just to make sure that you're, you know, being careful with those. We're not going to do that problem again though, okay? Now, we're not going to talk a whole lot about this, but we mentioned the normal distribution, which we looked at a little bit last year. Another measure of spread, though, that's related to standard deviation, but is really more a measure of spread for each value in the data, is this thing called the standardized normal variable, or the z-score. Okay? We have the standard normal distribution. Okay? Now basically what the standardized normal variable, or the standard normal distribution, does is it forces the mean to be 0 and the standard deviation to be 1. Okay? And what happens as a result, if this is 0, the z tells us how many standard deviations we are from the mean. Okay? So for example, if your mean, which to use the notation here, we use mu. Okay? Let's say the mean is 12. And your standard deviation is 2, okay? What score would I have if I were exactly 1 standard deviation above the mean? 14, okay? So, a raw score, the x's, and I'm actually going to kind of construct two different things here. We'll put x's down here, and we'll put z's up here, okay? A raw score of 14 would have a z-score of +1, okay?
Oh, and then it would be 16 and 2, 18 and 3, right?
Exactly.
Alright, cool.
And the reason why we do that is actually because if we're dealing with a normal distribution, we're able to figure out probabilities based on that. And that's what we're going to spend quite a bit of time doing in our second unit on statistics, okay? But I wanted to kind of give you a preview here. Yeah, if you have 16, that's going to have a z-score of 2. 18 would have a z-score of 3. If I had a score of, say, 10, that's 1 standard deviation below the mean, so that has a z-score of -1. Okay? 8 would have a z-score of -2, and so on. Okay? And you can obviously have fractions as well. If I had a score of 11, that would have a z-score of -1/2.
Ah.
Okay, I'm a half a standard deviation below the mean. Okay?
But wait, so then, how would you say that that's the standard deviation if the standard deviation equals 2? Or the
Well,
sigma sign is 2?
because basically what we're doing in this formula here, and we'll work with this formula even more in the future. Let me get rid of some of this. We're taking each score, say 14, we're subtracting the mean from it, so we're subtracting 12. That gives us how far away from the mean we are. okay? So we know 14 is 2 units away from the mean. By dividing by sigma, we get 1. That tells us how many standard deviations we are away from the mean. So this is the distance from the mean. This is the standard deviations from the mean. It's like a unit conversion.
So what's the Greek letter, that O at the bottom, that you're dividing by?
Oh, that's sigma.
Okay, so,
It's like a O with a hat on it.
right, so then I thought, sigma was the standard deviation.
It is. It is. It's like a unit conversion. 1 standard deviation equals 2 units. Alright? So if I have a distance of 2 units right here, okay? If I have a distance of 2 units, I want to convert that into standard deviations, okay? I need to multiply by a conversion factor. You could think of it this way. 1 standard deviation equals 2 units. You know, it's kind of like multiplying by 1 foot over 12 inches to convert from inches to feet. You know, so the units cancel out and I'm left with standard deviations. So it's 1.
Okay, so you just assigned that one standard deviation or 1 sigma was 2 units, you just
Yeah,
assigned that?
I just made it up for
Okay, so
data.
that's not like a rule?
No. Like if we were doing it with the dogs that we had earlier, what was the, just as a reminder, what was the standard deviation and the mean for those dogs?
The mean was 394.
And sigma was,
21,700.
That was the
oh yeah, we didn't find the standard deviation. Go ahead and square that 21,000, or square root
147.3.
147.3. Okay, so we'll just do 147 to do three sig figs. Okay. So, and then we had 5 pieces of data, right? So, someone read out our data for us, please. What were the 5?
600.
600?
Yeah. 470.
Okay.
170. 430. 300.
Okay. So, if those are my scores, then my z-score is x minus mu over standard deviation. So it's going to be 600 minus the 394 divided by 147. So it's whatever 206 over 147 is. Okay, so it's like 1.3 or something like that. Right? What do we get there? 1.4? Okay. So our z-score there, this is 1.4 standard deviations above the mean. One of the reasons why we do this is because for any normal distribution, we could figure out like what percentile the 600 is based on the mean and standard deviation of the whole data, of all the data. But by standardizing it, we can have one table for the standard normal distribution, and once we get the z-scores, we can just look at that table and say, oh, a 1.4 is the whatever percentile. Does that make sense? So, it's much easier to calculate a z-score than it is to recalculate those percentiles and the probabilities and stuff that we'll do later, okay? So again, like here, 470 minus 394 over 147, we'd get 76 over 147. Okay, so you'd get somewhere around 0.48 or something like that. Alright, so that's only about a half a standard deviation above the mean. Okay? And I won't do the rest, you guys can figure that out. Okay, the last thing I want to mention here is how we deal with grouped data. Okay? We have these marathon runners. Okay? When data's been grouped into classes, right? And this is important. When data's being grouped into classes, when we were doing the cumulative frequency graph, what value did we use as our x coordinate?
The highlights.
The highest, okay? So if we're doing cumulative frequency graph, we're using these values right here. Okay? If you are finding the mean or standard deviation, that is not the case though. Okay? We do not want to use that. We want to use instead, we want to use the midpoint of the class. Alright? So we're still going to have the frequencies being, involved here, but we have to use the midpoint for the class. So as I look at this data here, and again, we're just going to use the minutes since all of them finished within 2 hours. Or within the 2 hour something time frame. We need to find our standard deviation, we need to use x's that are the middle of the class. So for this first class, what would that be?
2 hours, 27 minutes.
Okay, the 27. Alright, we're just going to do the minutes here. So for the second one, it would be 29.
31, 33, 35, 37, 39.
Sabrina, you're just too smart.
And then what's this one?
44.
44.
41 less me.
Okay, and then 52. Okay? Everyone seeing how this works here?
Oh, that was.
Okay. So now notice our formula up here. It's very, very similar, but actually it's kind of like what you guys already kind of intuitively did this. Remember what Justin asked earlier? He said, if we've got a couple of 8s or whatever, can't we just do the subtraction and square it and then just multiply by however many there are? And I said, yeah, okay. That's exactly what this formula is telling you to do. Rather than doing the mean minus 27 8 times, okay, just do the mean minus 27, square it, and then multiply that by 8 as you're adding things, okay? Now, I already got the mean of 38 here, but remember to get the mean, oops, oh, I'm still on Zoom. Okay, to get the mean, we would do the sum of the score times its frequency all over the sum of all the frequencies. Okay? So if you remember here, what do we have? 69 runners. Okay, I think we had 69 runners total. Alright, so it's going to be over 69. But then we're doing 27 times 8 plus 29 times 3 and so on. Okay?
I have a question, so why are we, when is it not the midpoint that you use, but the highest point? Because we used that when it was cumulative frequency?
Yes,
Okay.
that was the case with cumulative frequency graph.
But when you're using it, when it's grouped into classes, so what is that in numeric, like standard deviation?
Finding standard deviation, finding the mean. If you're finding a value, you want to use the middle. Okay?
Okay.
If you're graphing if you're graphing that, then you're using the ends.
Okay.
Alright, so just to finish this one up, I'm not gonna finish finding the mean, because you guys can do that. Oop. I don't know why. Doesn't let you erase, but here we go. Try that. Alright, so what we're going to do, we need to take each of these and subtract them from the mean. So if the mean's 38, just to do the first one for example, we do 27 minus 38, square it, and then we're going to multiply that by 8. And then we're doing 29 minus 38, square it, and then we're multiplying that by 3. Okay? This is another case where the list might come in handy.
So should we erase what we've written before?
What do you mean?
Like
The mean thing?
This part.
You can. I was just reminding us how to find the mean when we have classes, or when we have frequencies. Okay? So we're going to do that with all of these all the way until the last one, 52 minus the mean, square it, and then we're multiplying that by 6. And the whole thing then, we would divide by the 69, alright? Now that gives us the variance, so that's sigma squared. Alright, so let's just take a look at this done with the lists again, just to help us, alright? We need to take the scores, which I stored in L1, so second L1, I need to subtract the mean. What did we say the mean was?
38.
38. Okay? Now, what do we need to do with each of those before... Well, what do we need to do with each of those next?
Add them up.
Before we add,
Multiply it by.
Oh, the frequencies, yeah.
what do we have to do before we do that?
Oh, square.
We gotta square it, okay? We've gotta square it. Now we have to multiply each of those by their corresponding frequency. This is another cool thing with lists. I stored all the frequencies in L2. So guess what? If I do this times L2,
So why do
Okay.
we need to square them before we do the frequencies?
because you want the squared difference, and then the frequency tells us how many times that is a squared difference.
How do we know definitively that 38 is average?
We did, we figured that out before. I started to do it, and then I said, you know, we had done this before where we had a frequency and a score. You multiply the frequency by its score and add all those up and then divide by the total of the frequencies.
But like, we never really knew the exact time, which was the score, you know?
But that's the thing, that's the rule for when we're dealing with class data like this where it's grouped,
You just take the middle.
we take the middle.
Okay.
So the mean, I mean, understanding that the mean is not going to necessarily be as reliable as if we had every runner's individual time.
Right.
It won't be as reliable, but it'll at least give us a good estimate. We're basically assuming that they finished on a normal distribution within each class.
Yeah, and there's no
Right.
skews or outliers
Yeah.
within each of the series.
Yeah. Okay, now look at this. I'm multiplying a list by a list. When you do that, it's going to multiply each corresponding item by the corresponding item, okay? So it's going to multiply 121 by the first thing in L2. It's going to multiply 81 by the second thing in L2. It's super cool, okay? So there we have it. Now I've got to add all those up. So I go to second list, come over here to sum. I want to take the sum of my previous answer. All right, and then
Divide it by 69.
divide that by 69, that's right. Okay, and what is that value? 50.88. What is that?
Variance.
That's our variance, okay?
So then the standard deviation, you just have to square root it.
Exactly, okay? So getting back to here, this whole thing here is what we just did. 50.88, which is then 50.9. I go back, and now I'm going to square root this.
7.133.
7.13. Okay? So now sigma, sigma is the square root of that 50.88, 7.13. Okay? So the standard deviation is 7.13 minutes in this case. Okay? And then once we start looking at normal distribution, we could say, okay, statistically speaking, 68% of the runners finished within 7.13 minutes of that 2 hour 38-minute time frame mean. And 95% of the runners finished within 14 minutes on either side of that mean. Okay, so that's where the normal distribution comes in. Okay? All right, so at this point, what I'm going to have you guys do, I gave you some extra practice on this document. If you go to your IP, your required IP document, you'll see what's actually the bare minimum requirement. Okay? Try some of these. We're going to take the rest of the time we've got here. I'm just going to let you guys work on these together and work your way through them, okay?